Good morning everybody. Today I'll start the lecture on gas turbine. So this whole week it will be like gas turbine, some specific nuclear power engines, some other type of engine also I'll try to discuss. So basically I'll focus on gas turbine engine. So gas turbine you may have seen in your aircraft engines. Whenever you fly, you see this wings will have engine. So that is basically gas turbine engine. You cannot use their IC engine or other type of engine because gas turbine is having some merit. In your naval ships also, especially um, Navy applications, there are several gas turbine engines used in many applications. So that's why I'll try to go through gas turbine engines, some basic calculation through this lecture. Okay, and for textbook, again you can follow the book Basic and Applied Thermodynamics, PK-NUG. That book is available in your library. And many websites also there regarding gas turbines, and there are big companies are there, for example Man Energy, then Pratt and Whitney, there will be Mitsubishi, several companies are there. And in India, if you say, then Gas Turbine Research Establishment, GTRE, of DRDO's laboratory, so they are also working on gas turbine. So they are trying to develop light combat aircraft and cavalry engine, many other type of engines. So gas turbine is a very important part for your civil life as well as military life or defense system. Okay, so in industry also lots of gas turbines are used. For example, your cogeneration gas power systems, or where you need electrical source for city powering, let's say continuous grid supply not possible. So in that case, you want to give local supply. So in that case, gas turbine can be used. Many big industries they will be using. So your aircraft engines, light combat aircraft or military vehicles, they can be using your INS and naval ships, INS class ships are there, warships. Those are also run by gas turbine engines. Okay, so here a gas turbine engine, or it is also an IC engine, internal combustion engine. So internal combustion engine we have seen it is a reciprocating type engine, but here we can see it is not actually reciprocating type, it will be continuous flow type engine. Okay, so that means I will have two type of IC engine, one will be reciprocating type, another will be continuous flow. So this is continuous flow IC engine or internal combustion engine. Okay, so it will be consisting rotary gas compressor, combustor, compressor driven turbine. So these three main part will be there in gas turbine. So many other part will be there, but we will not go through the details of everything, but the basic three thing: compressor, combustion chamber or combustor, and turbine system. So three system will be connected together and continuously gas or fluid will be flowing and you will get power. And here one example is there. GE Marine provides GT auxiliary equipment LM2500 to naval ships. So similar way, if you search GE, they are producing in the US based company. So they are producing lots of gas turbine engines for military applications also, but other companies also they are producing for military and civil applications. So gas turbine, you have seen aircraft. This one actually aircraft engine. Okay, so I'm giving a simple example because you have seen it. So aircraft engine will have, you may have seen this one, lots of blades will be there, you can see rotating, and shape will be like this, and gas will be coming out through this, right? So inside there will be gas turbine engine. So basic beauty is that more power to weight ratio. Okay, so this same weight, if you use IC engine or your Rankine cycle, that steam engine, their weight will be more than for same power output. But here we are getting more power for same weight. Okay, so it is having more power to weight ratio, not opposite, power to. Okay, especially light combat aircraft or civil or military aircraft systems, gas turbine engines are very much suitable because you are getting more power and where weight is lower. Okay, so this will be having thermodynamic process, like it will have one compressor system. Okay, so and one turbine system. It will be connected directly by a shaft. Okay, this is called compressor. This is turbine. I am putting C here, I am putting T here. Okay, this is turbine and this is shaft. Okay, so compressor will be taking air and this, after compression, this air will go to combustion chamber. Okay, from combustion chamber it will go to turbine, it will be exhaust. Okay, this is the simplest gas turbine engine. This is called Brayton cycle. Okay, this is called Brayton cycle. Okay, so Brayton cycle will have isentropic compression. So here then you have to draw one TS diagram when I was saying isentropic compression or something. So pressure will be like this. So compression isentropic 1 to 2, here 1, here 2, here 3, here 4. Okay, 1 to 2 compression is happening. So in TS diagram, if you see 1 to 2 vertical line I am showing isentropic compression. Okay, then 2 to 3 what is happening? Same pressure maintaining and you are burning. Okay, in combustion chamber from compressor to turbine pressure will be same actually. The combustion will be happening inside combustion chamber. So that's why this isobaric process, then 2 to 3, u raised to 3 means where combustion output will be reaching to turbine. So 3 to 4 your turbine part, and 4 to 1 many books they will be putting one complete cycle, but if you see aircraft gas turbine engine, this type of engine, it is not a complete cycle actually. Burning happening, exhaust happening, then the same gas you cannot put in your compressor because oxygen is not there, only flue gases are there. Okay, but that gas, high temperature gas, can be used for other purposes, later purposes we will discuss later. So basic cycle is that it must have one compressor, one turbine, one combustion chamber. Turbine will be connected to compressor directly. Why? Because compressor needs some power, because the compressor must be rotating. If you want to rotate compressor, some power required, so directly that power will be coming from turbine. Okay, so in TS diagram it will be like 1 2 3 4. Okay, this is basic simple system. So we will draw this one in PV diagram. So in PV diagram, compression happening first, let us say 1 to 2 compression happening, axial compressor you have, then 2 to 3 constant pressure process. Okay, 2 to 3 is constant pressure process, this is constant pressure. Okay, this is also constant pressure line. So combustion is happening at constant pressure. Okay, so 1 to 2 pressure increasing, volume reducing, then 2 to 3 constant pressure. Okay, 2 to 3 constant pressure process, then 3 to 4 what is happening? Expansion happening. Okay, so 3 to expansion happening, so it is like this. Okay, now 4 to 1, this is 4. Okay, 4 to 1 actually exhaust process. This is a constant pressure process. For example, if your gas is going to atmosphere, it will be atmosphere pressure, right? So that's why there is no pressure change. 4 to 1, it is constant pressure process. So this is isobaric process. So I have two isobaric process, 4 to 1 and 2 to 3. Isobaric 4 to 1 and 2 to 3. Okay, and isentropic happening 1 to 2 and 3 to 4, 1 to 2 and 3 to 4. Okay, so I have 4 processes. Isentropic compression. Okay, you see this typed text. Isentropic compression is there. Isobaric combustion is happening constant pressure. Isentropic expansion, isobaric heat rejection. So this is actually ideal cycle if we want to do practical cycle. For example, in Rankine cycle we have seen, if we want to draw a practical cycle on PV diagram or TS diagram, so some small changes will be there. For example, if I draw this one as, so actual cycle TS diagram or PV diagram, if I do whatever you say, okay, 1 2 3 4, this is ideal. Practically compression power requirement will be higher and your turbine power will be lower, 2 dash 4 dash. Okay, so actual 1 2 dash 3 4 dash. Okay, and ideal 1, 2, 3, 4. Okay, you see the difference. If you go for actual, then actually you are giving more power to compressor and you are getting less power in turbine. But in ideal case, you are getting more power, so isentropy process. Okay, and whenever you are saying actual process, I draw the lines in dotted form. Okay, dotted form, that does mean that it is a irreversible process. Okay, actual process is irreversible process, that's why I draw dotted line. Okay, when I say isentropic, I'll be drawing solid line. So you also, when you are writing an exam, so you write solid line for isentropic and dotted line for your irreversible process where energy loss is happening, entropy increasing. Okay, so you can see one gas turbine engine, whatever I have drawn actually you can resemble. Compressor was there, then shaft was there, then turbine was there, then one combustion chamber, entry and exit, 1, 2, 3, 4, the process. Okay, and it is open cycle actually, because gas entry, same gas is not going back to your compressor. Okay, in many cases for simplification people will be adding 4 to 1, but practically it does not happen. Okay, because same exhaust gas, burned gas, that is not having any oxygen, that you cannot put in turbine compressor again. Another issue is that gas will have a higher temperature. So higher temperature gas you are compressing is not suggested. So air atmospheric temperature will be normally 30 degree around. So if you go to a aircraft engine upper atmosphere, their temperature will be much lower, but normally say Chennai temperature 30-35 degree. So that but exhaust gas temperature will be much higher. Okay, so lower temperature gas compression is easier than higher temperature gas compression. Okay, so we will be taking atmospheric air for compression. Okay, then we will be compressing, burning, exhaust, done. Now I will resemble this one. So air intake is happening here. Okay, so this one I can say 1, I can resemble this part. Okay, air intake is happening here. Then my compressor stage, you can see this one. Okay, low pressure. So several stages of compressor will be there actually. When if you see gas turbine engine, so several stages of compressor, several stages of turbine will be there. Okay, here also you can see 1, 2, 3, 4, 5, many stages compressors are here actually. Okay, so several stages compressor will be there. So altogether actually you can resemble 1 to 2. Okay, 1 to 2 process is your compressor. Then where is your combustion chamber? So here actually combustor is there. This is called combustion chamber or combustor. Okay, combustion chamber. Then your turbine section. Turbine section again expanding. This is turbine section. Okay, so you can see compressor gradually area reducing, then combustion happening, then again expanding. So this actual picture, if you Google it, you will find lots of gas turbine actual engine picture also. Many companies, those are going for business, they also put their own compressor system picture. So you can see that one. Okay, so compressor gas compression happening, combustion happening, expansion happening. So the same thing will be happening for your aircraft engine or your marine engine if you are using gas turbine system, or this can be used for your other industrial applications. So compressor, they are saying another term is there, gas generator. So you are not generating gas, actually you are compressing, but people use the other term gas generator. And axial or centrifugal or combination of two can be used. So normally first stage will be axial compressor. Why axial compressor? Axial compressor actually they can handle very large volume of air. Okay, you can remember the pump turbine I was teaching that time. So axial machine will have very large volume handling capacity, but low pressure handling capacity. Okay, so first stage normally it will be having axial type. So you take large volume, you compress a little bit, then you go to centrifugal and other type. Okay, maybe axial or centrifugal. So first stage should be axial type, take large volume, compress it, reduce volume, then put into a centrifugal or maybe next stage of axial compressor. So here also you can see 5 stage low pressure compressor is there, then again high pressure compressor is there. So low pressure compressor stage normally it will be axial, then high pressure stage when you are going it may be axial or centrifugal. Okay, so many compact engine people they will be using centrifugal type, because centrifugal they can develop very higher pressure, okay, but low volume handling capacity. So in that case reduce volume using axial system, then put in centrifugal system, then you compress, you increase oxygen density. Actually when you are compressing, you are giving more oxygen, small volume, put into a combustion chamber. The air goes to combustion and annular can, okay. So this combustor system I will discuss later. Annular, can annular, different type of combustion system is there. Roughly 70% of air from compressor is ducted around the combustor for cooling purposes. So combustor actually it is burning, fuel will be burning and temperature will be very high. So very high temperature and material strength will be a problem. So outside that combustion chamber or combustor, lots of air will be flowing, so that lots of heat will be carried away, otherwise it will be melted, the combustion chamber. Okay. 30% mixes with fuel and ignited and ignites by burning air. Okay, so 30% air will be used for burning your system, that fuel. Remaining will be just for cooling purposes. The burn gas expands in turbine annulus, that's fine. 60-70% power used for the gas generator. Okay, so a good amount of power is used for your compressor system. Gas generator means compressor system. Gas turbines are less complex than reciprocating engines because it is having only one shaft. Okay, one shaft. Compressor is here, turbine is here. So compressor compressing, turbine rotating. So it is giving directly power. So there is no other moving element. Only this one shaft connected your compressor system and turbine system rotating. So it's a very simple system actually. Okay. So gas turbines are less complex than reciprocating system. Basically on the central shaft is rotating part. Okay, central shaft is only rotating, other but you reciprocating system, you can remember when piston is moving up and down, your crank is moving, connecting rod is moving, then your fuel injection system, they will have continuous jerk flow, the continuous flow fluid you cannot give inside, even a valve also will be opening closing. So lots of moving element is there. Any mechanical system, when moving element is more, life and reliability will be lower, it will be requiring more maintenance. When there is no moving element or very limited, your life will be longer. Okay. So gas turbines are less complex than reciprocating engine because it is not having continuous opening closing valves or cam mechanism to move up and down, or crank or gudgeon pin or piston, nothing is there, right? Okay. Other small moving parts are in the fuel system. So fuel system will have some small moving part, but that is also not major thing. Advantage of gas turbine is the power to weight ratio. Okay. So it will be giving more power for the same weight. Thrust journal bearing. Okay, so it will have several bearings. Later we'll discuss different types of bearings and journals. Okay, so that I may not cover in this week, but I'll be considering this thrust bearing, journal bearing later when I'll be discussing about power transmission system from engine to propeller. So gas turbine engine, I already told, compressor is must. Again, I'm drawing in certain way, so you should not draw in opposite way, or you should not do any mistake, otherwise I may not give you marks. Okay. So compressor means volume reducing, that's why this is converging nozzle, converging type shape, and turbine diverging type shape because volume increasing. Okay. And this same diagram actually you have drawn for your steam turbine also. There steam was expanding, here your burn gas expanding. So here you are not using water, here direct whatever burn gas you are getting, the same gas is running your turbine. So very high temperature is there. Okay. But in steam turbine, you produce steam, you took water to produce steam, that steam was running turbine, where here I am not using any water. My burn gas directly hitting turbine blades and turbine blade is getting energy. Okay. So most gas turbine compressor axial flow multi-stage, already you have seen. So here one picture I have taken, it is there in Wikipedia also, how this turbine blade will be there, one rotor blade, one stator blade, rotor blade, stator blade, this way it will be rotating. Okay. Gas turbine compressors typically have multiple stages. Each stage contributes to a portion of the overall compression rate. So in pump system also you have seen that each stage will be developing certain amount of pressure, certain amount of pressure, certain amount of pressure. In pump we said head, but here we say directly pressure. So how much pressure are you increasing? Next, so one stage may be 1 bar, again 1 bar, 1 bar, so multiplied. Okay. So that way multiple stage will be helping. Pressure ratio, here I am writing P ratio means pressure ratio actually. Those girls are speaking, don't speak, don't speak. Okay. So the pressure ratio is P discharge divided by P inlet. So outside pressure here P discharge may be P discharge, P inlet. So this ratio is called pressure ratio. So how much pressure is required, based on this formula you can calculate. Okay. Inlet guide vane controls the angle of direction incoming air. Okay. So whenever you are talking about multiple stages in maybe in compressor turbine, so let's say one stage will have some airfoil. Okay, airfoil will be getting fluid, it will be diverting, then again you need another airfoil to redirect the fluid to another blade. Okay, so there will be one blade system called guide vane or stator blade. Okay, so guide vane or stator blade purpose will be to direct the flow to next blade. Okay, so I'll discuss later about this one in details. And cooling air may be blade from the compressor to cool component, ensure their longevity. Okay, so cooling air also will be required to cool systems, like say gas turbine combustor also was getting 70% air, right? And some cooling air will be required for turbine blade cooling. Later we will discuss how to cool turbine blade, because combustion, the burnt product will have temperature more than melting point of the blade, but still blade should be surviving. So how to survive that blade within more than melting point environment. Okay, so we'll discuss later. The compressed air mixes with fuel in the combustion chamber. Okay, this is obvious. Okay, so flow through stages, how it is working. So let's say first stage turbine blade is here. Okay, many turbine blades are there. For example, this 1, 2, 3, 4, many blades are there. Okay, so and fluid is coming here, fluid is here, fluid is okay. You can see this airfoil. Actually, these blades are actually airfoil. These rotating blades are there. These are actually airfoil cross section will be there. Okay, so one airfoil from top, if you see like this, it will be like this. Okay, each blade. So here also these blades will have this type of some shape will be there. Okay, it is not looking like any airfoil shape, but normally there will be airfoil shape. Okay, when airfoil shape is there, let's say air is coming from here, air will be getting diverted, it will get proper angle. Again, this is, let's say, stator, rotor blade, stator blade. Okay, so what is happening, the stator blade will be diverting fluid so that rotor blade will get proper angle. So you can remember the angle of attack. So any airfoil, if it is not getting proper angle of attack, let's say this is your chord line and fluid is direction is here. Okay, so this is called angle of attack. So all the airfoil should get proper angle of attack. Okay, if angle of attack is very low, it will not get any power. If angle of attack is very high, again it will not get power. So you should have an optimal angle of attack for any airfoil. Okay, so you can remember the lift. So blade will get lift if you have proper angle of attack, like 10 to 15 degree about, angle of attack will be there. But in any case, if fluid direction changes and angle of attack become 50 degrees, 60, 100 degree. So in that case, blade will not get proper angle of attack, so it will not give proper force to the blade. Okay, so that's why, let's say one airfoil is here. For example, let's say I have one airfoil like this. Okay, so airfoil fluid is, let's say fluid is hitting this angle, perfectly fine, but if fluid is hitting in this angle or this angle, so it will not get proper power. So what you have to do, so you have to give another level of airfoil here, so that will be directing fluid towards this with proper angle. Okay, so here also you can see my stator blade is giving actually the direction that task they are doing. It will be in proper direction, so that my rotor blade, which is harnessing power, so rotor blade is harnessing power. Okay, so turbine blade will be like one rotor is there, one blade, two blade, three blade, four blade, five blades, 36 blade will be there. Okay, 36, 35, many number of blades possible for different types of turbine. Okay, so stator blade will be giving angle only, it will not be harnessing any energy. So it is fixed blade, it is directing fluid. Now I will have here rotor blade. So rotor blade will be harnessing energy. So rotor blade must get that proper angle. So stator blade purpose to give proper angle, not to harness any energy, not to do anything. Okay. Then my rotor blade will be harnessing energy, so it must get proper angle. After exiting from rotor blade, again fluid will be diverted here and there. So again I will have another level of stator blade. It will be redirecting with next stage turbine blade. So one stator, rotor, stator, rotor, stator, rotor, that assembly will be there. So one stator, one rotor is called one stage. Okay. So one rotor, one stator rows called one stage. So here I can see here rotating. So this is one stage. This is rotating and unrotating part actually here. I cannot see here. So here rotating, unrotating. So 2 stage. So 3 stage, 4 stage. So I have 4 stages actually. This rotating part you can see. Okay. So one rotating, one unrotating or static or not rotating part. So together call stage. Okay. So stator will not harness any energy. It will direct fluid to give proper angle for rotor blade. After rotor blade, fluid will be diverted here and there. Again stator will say, hey fluid, be in proper direction. Then rotor will be harnessing again rotor will be harnessing. So rotor will be connected on one common shaft and rotor will get total power. Okay. So compressor or turbine, whatever you say, same mechanism actually. Rotor, rotor stator, rotor stator, rotor stator. Stage 1, stage 2, stage 3, stage 4. So all together total power how much we are getting, we can calculate. And again in compressor, first stage rotor height will be higher, because first stage compressing little bit, again little bit lower, little bit lower, little bit lower, little bit lower, because compression happening every time, right? So that's why you can see my compressor I have drawing, I am drawing here like gradually decreasing, because compression is happening. Okay. In turbine what is happening, initially we get very high pressure gas, you stage 1 little bit expanded, expanded. When it is expanding, it is giving some energy to rotor, not stator. Okay. My stator will not harness any energy. You will say, okay, you take fluid, I am guiding you. Okay. Rotor will take energy. Fine. So then one stage means one rotor and stator, and stator blade guiding, rotor blade harnessing energy. Fine. Okay. Now one more thing I have to explain here, that compressor if I draw properly, actually it will be like looking like this. My casing is here, my compressor not like this, it will be like this, compressing. So let's say one stator, rotor, stator is here, rotor is here, again stator is here, rotor is here. Okay. So one stage, okay, gradually you can see one stator is connected to my casing, so that stator will not be rotating with shaft. Okay. So this stator I am shading only, just you can see. Okay. The stator is connected to your casing part, outer casing, that is not rotating. Okay. Rotor is connected on shaft. So rotor, when it is getting force from fluid, it will be rotating my shaft. Okay. So that means my stator is not giving any power, it is just fixed. Okay. So this way you can see this compression happening and my dimension also going down. Okay. Next is combustor. I told that after compression, the gas or air, compressed air will go to combustor. Okay. So combustor or combustion chamber. So combustor, different types of combustion chambers will be there. Like here one picture, right side top corner, you see this combustion chamber. Actually here they will get fuel air mixture and air will be entering. Okay. Combustion will be happening. From there the turbine blade. This is a turbine blade. Okay. This is a compressor. This is shaft. Okay. So compressor, air will be entering to combustion chamber, burning will be happening, then it will go to turbine, and compressor will get power from shaft from turbine directly. Okay. So just I've copied from Pratt Whitney, actually the compressor manufacturer company, big company actually, so from their website. And left side you see this NASA from NASA website I have taken different types of combustor section, because that combustion will be controlled combustion. You cannot give random combustion here, one spot very high temperature, another spot very low temperature. It must be okay. So combustor will be giving uniform flow with uniform heating, uniform pressure. So that's why they'll be putting like can combustor or annular combustor, annular or ring type combustor will be there. Can means like small things are there. You can see these small cans. So combustion will be happening 1, 2. So many cans will be there all around the shaft. Okay. In annular, if you see, then one continuous combustor will be there. So that will be delivering high pressure fluid to your turbine. High pressure fluid means combustible burnt gas, flue gas. So in boiler case, actually flue gas was going out. We are not using actually for turbine running purpose. We are using the heat, that's fine. But in this case, the same flue gas we are using for running turbine directly. Okay, no water is there. Okay, so burners endure high temperature, consist of outer casing. Outer casing is here, outer casing. Okay, and it will be facing very high temperature because combustion is happening here only. Okay. So modern gas turbine contains 3 combustion design, maximum temperature limited by the rotor and nozzle guide vent material, typically 850 to 1600 degrees centigrade. So normally steel and other material temperature melting point will be 1200 around, but you are getting combustion temperature 1600. That means you must have some cooling arrangement, otherwise heat will be accumulated and your system will be melted. Things will not work.